Good afternoon, ladies and gentlemen. Welcome to this Spotlight Talk series. My name is Boelo Schuur. I'm Scientific Vice President of the European Federation of Chemical Engineering, the EFCE. I have been in the board of the EFCE since January 2024. I'm a chemical engineer by training, and I have received my degrees from the University of Groningen in the Netherlands. I have stayed all my career in academia, except for a small excursion as a side job. But my main affiliation has always been in universities, and currently I'm in the University of Twente in the east part of the Netherlands, where I'm currently a full professor, and my chair is called Sustainable Separation Technology. I'm very happy to be involved in the introduction of this webinar on membrane engineering, and more specifically, membrane engineering for a circular economy. I'm looking forward to participating to it, and my role is to introduce the Spotlight Talks concept and also the EFCE, which I will do now. Let me start with the Spotlight Talk series. Several years ago, during the COVID pandemic, the Spotlight Talk sessions have been initiated as the only way we could convene at those days. And based on the success of these sessions, we have decided to continue it also in years where we do have regular conferences again. And now for this year, we don't have a big European conference on chemical engineering. And so we will have both a spring session that is currently ongoing and a fall session. This spring, we will have 9 Spotlight Talk sessions organized by 11 of our working parties and sections. From yesterday through the 17th of March, we may enjoy these short sessions of typically 3 talks focused on a specific subject and by leading industrial and academic experts. The complete program is available on the EFCE website, and you are encouraged to explore the other sessions as well. Now, a little bit about EFCE. The EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries and representing more than 100,000 chemical engineers all over Europe. Our working parties and sections cover all the major aspects of chemical engineering and are the core of our organization. They form the scientific engine that drives many of the EFCE's activities. It's an important forum for technical exchange and networking. And in each of our working parties and sections, highly skilled engineers from both academia and industry gather. I would like to invite everybody to have a look at the website of the EFCE at efce.info to explore our scientific groups, and maybe you are interested in joining one of our sections. Joining a working party is an invitation, but if you see that your country is underrepresented and you feel that you are a potential representative, you could contact your country organization and maybe the working party individually, and then explore whether there would be opportunities for you to participate in EFCE activities. So before concluding, I would like to thank all the people who have worked hard to make these complete sessions possible. And today we have the session on membrane engineering, and I would also like to thank Martine Pou for organizing everything from her base in Toulouse. I would like to thank you for your attention, and I wish all the speakers and attendees a fruitful and successful webinar. And I would like to give the word to Alessandra Criscuoli, who is the chair of the section on membrane engineering, to introduce this section to you and also the speakers of today. Alessandra, the floor is yours.
Thank you very much for the kind introduction, Boelo, and good afternoon, everybody. I'm Alessandra Criscuoli, a researcher at the Instituto of Membrane Technology in Italy, and currently I'm chairing the EFCE section on membrane engineering. My background is chemical engineering, and I'm working still on chemical engineering, but applied with membranes. And in our section, we just focus on the possibility to apply and to disseminate and to promote the science and technology related to membrane engineering in particular. So we are focusing on this specific approach. And today I'm pleased to welcome all of you to the Spotlight Talk on Membrane Engineering for Circular Economy, organized by the EFCE section of Membrane Engineering. And I would like to give you some information on this talk. Why this topic? Well, the topic of the talk arises from the worldwide need to minimize waste production and raw sources depletion. And both goals can be reached by reusing and or recycling materials and products in the logic of a circular economy rather than a linear economy where a product after it's used becomes a waste following the scheme of extraction, production, consumption, and finally disposal. And this means the development and application of technologies able to separate and recover the species of interest from waste streams, as well as rethinking the end of life of products. So in this context, we think that membrane operations can play an important role. In fact, they can be applied to valorize streams, to the selective separation of specific compounds to be reused or recycled. However, also membranes have some issues. For example, after their lifetime, membranes must be disposed and the end-of-life treatments need to be defined. So in this respect, today we will learn about the application of membranes for the recovery of species of interest from different streams, as well as the cradle-to-grave path of nanofiltration, which can be considered a sort of life cycle assessment of this well-known membrane operation. And in particular, we will have 3 lectures given by experts in the field, and I thank them very much for their contribution and to be here with us today. And before starting, I would like to remind to participants they cannot talk directly with the speakers, but they can type their questions in the chat so that speakers can reply at the end of their presentations. So this is the main aim of this day and this afternoon, so we can move to the first presentation. And it's my pleasure to introduce Professor Gyorgy Szekely from the King Abdullah University of Science and Technology, KAUST, in Saudi Arabia. Also, if we know that today is from US speaking. And he will talk about the circularity in nanofiltration, so from building blocks to end-of-life treatments. Please, Gyorgy, the floor is yours.
Thank you. Thank you very much for the kind introduction and also for the invitation. I really appreciate it. Hopefully you can see my slide now and you can also hear me. Okay, perfect. Okay, so the title of my presentation is Towards Circularity in Nanofiltration, from Building Blocks to End-of-Life Treatments. And I will try to give you an overview of the different aspects of nanofiltration and the sustainability of nanofiltration that my group has been focusing on in the past 5 years or so. Trying to move my slides. Okay, perfect. Okay, a little bit of introduction. So my group is called the Sustainable Separation Engineering Research Group, and we have different components that we are focusing on. So we try to combine chemical engineering, polymer chemistry, and material science, and recently data science, to make separations less energy efficient and more sustainable. So as you know, membranes in general have several different benefits compared to other separation processes. But we have to make sure that not only the membrane processes can contribute to sustainability, but also the way we prepare membrane materials and how we treat them at the end of their lifetime. Okay, if you're interested in this topic, then I recommend you to read this recent perspective article on the 12 principles of green membrane materials and membrane processes that you can see here on the left and right-hand side, and their interconnectivity. This is my personal perspective on this topic. So people may argue that there should be more points or there should be less points. But I think both of these lists give you a fairly good overview of how to approach membrane material fabrication and disposal, and how to approach the use of membrane processes to maximize their benefits. So if you're interested in this topic, then I recommend this perspective article in RSC Sustainability. And in the interest of time, I'm not going to go through all these 24 principles today, but rather try to give you an overview of our contributions in terms of research efforts over the past years. In this perspective, you can also find a roadmap how to address the different sustainable development goals of the United Nations. So here you can see the 3 pillars of sustainability in general. What are the key membrane contributions to these pillars, and how they are connected and how they are helping us to realize the different UN SDGs. Okay, so now let's talk about membrane materials. So here you can see the linear approach, where you take some fossil-based resources, you use toxic solvents, you prepare a membrane material, then in, let's say, organic solvent nanofiltration, you need to cross-link these materials to achieve solvent resistance, or you can do other types of surface modification for different purposes, such as membrane reactors. Then you use the membranes in different applications, filtration, catalysis, and so on. And at the end of their lifetime, you have to dispose them, which results in incineration, microplastic pollution, and so on. So the idea is to follow the principles of circular carbon economy, where you take natural resources, you use green solvents, you prepare a green membrane material. And then ideally, with mild conditions, you can do some surface modification. You use them in energy efficient separation processes. And at the end of their life cycle, you can dispose them, recycle them. They can go back to nature, or you use them again. So what are the different criteria that actually define whether a membrane is green or not? Here you can see a list of different contributing factors, such as the monomers that you use for your TFC fabrication, the solvent for your phase inversion or the dissolution of your polymer, the support material that you're using, the polymer itself, and of course the approaches for reusing and recycling, as well as biodegradation. So here you can see a list of different chemicals that were traditionally used for the fabrication of TFC membranes. These are mainly amine-based monomers in combination with acyl chlorides that are often toxic and undesired in the sense of sustainable development. And here on the right-hand side, you can see many examples from the literature where different amine or hydroxyl-based natural compounds or building blocks were used to fabricate membrane materials. And here I'd like to note that the raw materials that are coming from nature are often having a lot of hydroxyl groups that you can see here. But identifying building blocks with amine groups, such as the one here and here, are less frequent. So here is one example that we worked on in the past to prepare hydrophobic TFC membranes using only green resources, which includes monomer 1, in this case tannic acid, and monomer 2, which is priamine, that you can see here. We used a recycled PET porous support to prepare this thin film composite membrane. And we were also using green solvents. In the first case, it was water. In the second step, we used paracymene. So here you can see the characterization of the membrane. This is the initial porous support from the recycled PET, which was actually prepared in collaboration with Professor Nunes at KAUST. And they prepared this PET support with high surface porosity of about 7%. And with a contact angle of about 59. And here you can see that after the coating and the preparation of the thin selective layer, we managed to achieve a hydrophobicity with a contact angle of 98. And the pores that you initially saw at the surface of the support is already gone. The thickness of the membrane was about 20. I think we managed to prepare this between 10 and 100 nanometer with respect to the selective layer. Here you can see about 30 nanometer for this particular membrane. And we looked at the reaction time, the preamine concentration, and the tannic acid concentration, and identified how these parameters that we can vary actually affect the performance of the membranes and the characteristics of the membrane materials. Then we looked into how to quantify the sustainability or the greenness of these membrane materials. And up to this point, there was not much information and quantitative measurements of these aspects. So what you can see here, it's very difficult, by the way, to compare the sustainability or greenness of membrane materials. So we looked at the total mole number used in the fabrication of the membrane materials, and here is a summary of more than 25 different literature papers on petroleum-based TFCs. And here you can see the score of our membrane. And here you can see a more fair comparison, focusing only on so-called green TFC membranes reported in the literature. And here we are still quite competitive and scored second compared to the reference number 4 in the literature. We also looked at and developed a pictogram-based semi-quantitative comparison for the greenness of membranes that you can see here in this table. So here the idea is that the area of these pictograms that you can see here is normalized. In this case, it's 1 millimole of the chemical in 100 milliliter of solution. And each row represents one literature. In this case, the first one is our paper on the tannic acid with preamine. And here you can see these tiny pictograms and how they compare with other literature materials. So here, this gives you an immediate feel for which process to go for, which chemicals to use. It's not only the size of the pictograms that matter, but also the number of the pictograms. So here we only have 2 hazards, for instance. In our case, we had 3 hazards. In this particular case, a lot of chemicals was used to fabricate these membranes, whereas, for instance, here and here, much less. We also quantified the solvent consumption that you can see here and compare them and the cost of the solvent. So there is a misconception that green solvents are more expensive and therefore prohibited in industrial settings. Many of the green solvents, they actually have competitive prices and they are not that expensive. However, some of these solvents that are bio-based, they are less stable than fossil-based solvents. So that could be one issue in terms of scale-up and reproducibility. You also need to consider that when selecting a green solvent. Okay, now let's move on to the second example. This is about an ultra-stable Janus membrane made from dopamine. So dopamine is a very well-known coating material, and it has also been used to adjust the pore size of membranes, but they were always applied as a post-fabrication treatment for membrane materials. Reason being, dopamine, when it polymerizes, it forms small nanoparticles or microbeads in some cases, depending on the additives, but they are not film forming. They don't have a film forming ability. So we started to look into this, and we made a serendipitous discovery where the combination of dopamine with different diamines actually yielded freestanding films. And then we started to explore what are the different characteristics of these diamines that result in stable films that can be used as membranes. And when there is no diamine, then we obtain these nanoparticles. When the chain length of these aliphatic amines, diamines, are short, then we get fragile films or membranes that cannot be tested for filtration. If we use aromatic type diamines, then we get crystals rather than films. And then we identify that with sufficient chain length, we actually can obtain stable films. And then we looked into the application of these freestanding films, and they are not only suitable for nanofiltration, but they can also be used as a double-sided or single-sided biotape. And we demonstrated that using different type of materials that were glued together. So then we wanted to understand what is the reaction that is going on between dopamine and these diamines. So we started to investigate different mechanisms, and we narrowed it down to the imine formation and the Aza-Michael addition. And then at the end, the modeling that we have done, and also the stability of the films in concentrated hydrochloric solutions, hydrochloric acid solutions, we concluded that it is the Aza-Michael addition supported by all of these experimental and in silico results. Then, of course, we looked at the chemistry to back this up. We also looked at the effect of the carbon chain length. We have done standard characterization on these membranes. We looked at the permeance in conventional solvents that you can see in black here, and also in green solvents, trying to promote the application of green solvents, not only in the fabrication, but also in the processing using membranes. Here, I'd like to highlight the results here, because often I get the comments that bio-based membrane materials might not be as stable as fossil-based membrane materials, but that's not always the case. So in this particular study, for over 3 days, we managed to get a fairly constant permeance and rejection using our membranes. Here you can see the results for the biotape or a bioadhesive. And I like to highlight this particular result, that with most of the commercial tapes, we have a competitive performance. So again, I would say that the bio-based tape can compete with many of the commercial materials. Here's another example. This project we did in collaboration with Professor Chen at the Colorado State University. They are experts in polymer chemistry, and they came up with the idea of using this natural monomer that you can see here. And with an organocatalytic process, we can obtain these polymers. So then we fabricated membrane materials from these circular polymers. And here we have 2 options for the end-of-life treatment. We can do enzymatic biodegradation, and then it goes back to nature, and through bioregeneration, you can obtain this monomer again. But we also explore the more direct approach, where we take the membrane material, we have to clean it first, but then we can perform organocatalytic depolymerization to obtain these monomers in a pure form confirmed by NMR. So this means that we can again build a polymer from it and use it for different purposes, make membranes again, or use it in different applications. And I'd like to highlight that both the polymerization and depolymerization can be performed under organocatalytic conditions, which is again in line with the 12 principles of green chemistry, actually, because we are not using any of the toxic metals usually needed for these type of reactions. Okay. There are two different ways of polymerizing this monomer, giving two different polymers, and we actually looked at both of them and prepared membrane materials. This resulted in two different publications. If you're interested in these type of circular polymers and membrane materials, then I suggest these two JMS letters publications from 2022 and 2024. Okay. Then we wanted to compare the different membrane materials that were fabricated using biomass. And here you can see a qualitative comparison of these materials. So here is where agricultural waste was used, here shrimp waste, seaweed, palm oil, mill effluent, corn cob, and algae. And what you can see here is the comparison in terms of the number of solvents used, chemicals, and the processing steps to obtain these membrane materials. And here we were focusing on the use of algae biomass to prepare membrane materials. And here the idea was that we realized in the literature most of the membranes prepared from biomass resources, they first had to go through an extensive purification with multiple steps to obtain monomeric material or a highly pure polymer before that was turned into a membrane material. So the idea here in this project with the algae was to prepare these membrane materials using raw biomass. And if we manage to make membranes from raw biomass, then of course we need much less processing steps, energy, and much less resources in general. We also compared the different membrane materials and their performance in terms of permeance and, in this case, styrene dimer rejection. And what you can see here that all these literature data and our own data scatters quite well on this plot, which means that we can have membranes with higher permeance and, of course, lower rejection, or higher rejection but lower permeance. So we can select the right membrane for the application that we are interested in. And here you can see the concept for this algae-based approach. And this project was done in collaboration with Kyle Larson, who's an expert in the modification of the genetic engineering of algae. He's making algae to produce whatever he needs. In this particular case, he was using algae to clean up wastewater, and then the NPK-rich effluent was used to grow algae, and that was producing methane. And at the end of this process, they have algae biomass that they don't know what to do with it. And traditionally, algae biomass can be used as an animal feedstock, but we can find more advanced applications of these biomass resources. So in this particular case, we were trying to react the algae biomass with different chemicals. And the one that was actually working is TMC, which is an acyl chloride. And I was advocating against acyl chlorides. But in this particular case, we had to use the second monomer as TMC. Otherwise, there was no reaction and film formation. And we used the green solvent parathymine in this particular case. We were also interested in understanding whether this raw biomass and the membranes that we derive from it, they are the same if we use clean water or we use the wastewater algae source. And when we looked at the performance of the membrane and the characteristics, we realized then the source of the algae biomass actually matters. And in some case, we get thicker or thinner membrane materials, and the performance also changed based on the source of the algae. So here it's quite important to keep the conditions for this biomass consistent if we want to have membrane materials that are also reproducible. So when we move from clean raw materials to crude biomass-based raw materials, then the reproducibility really depends on the source and the pretreatment or the previous life of that biomass. And here I would like to also mention one of the applications that we looked at with Kyle. So in this case, he was developing algae that can produce potulol. And potulol is a super expensive compound used by the perfume industry. And he wanted to concentrate it up because the algae produces it at a very low concentration. And initially, they started with commercial membranes, and the petulol was just going through the membrane. It's a relatively small compound. I think it is about 250, 300 Dalton. So then, as I said, we are also interested in data science and machine learning, and we established the OSN database. So you can go to www.osndatabase.com, where we have different data sets that you can freely download and use. And we also provide different machine learning based tools for the prediction of membrane separation, energy intensity, and so on. So using these tools, we identified that the best rejection for potulol was actually in the case of methanol as solvent. So they grow algae in water. The algae secretes the potulol into the aqueous stream, but then we need it in methanol to be able to concentrate it effectively. So we've developed this process that you can see here, where we do membrane contactor here. We use membrane contactors to extract from the aqueous stream into dodecane. From the dodecane, we go into the methanol phase. And then we can use a Duramem 300 membrane nanofiltration module to concentrate the potulol. We looked at the different environmental factors and economic sustainability and solvent consumption to compare different process scenarios and also compare the original synthetic route that was patented. So what you can immediately see from this graph is that the original patented synthesis of potulol has an enormous environmental footprint. Here you can see all the different membrane configurations that we were looking at, such as the use of methanol, the use of a single-stage nanofiltration, 2- or 3-stage nanofiltration, the implementation of dodecane as the extraction solvent. And you can see that all of these approaches, no matter which one you choose, will significantly reduce the environmental burden for this process. Okay, so I would like to wrap up the presentation here. What I presented today gives you an overview of what are the different types of raw materials and monomers and polymers that can be used to fabricate membranes in a greener fashion. We also looked at end-of-life treatment of these membranes and the option for depolymerization. After the cleaning of the membrane material, then you can reuse these monomers to fabricate membranes or for other purposes. We also looked at the application of these membranes in the concentration of potulol, which is a natural compound, but currently it's very difficult to concentrate and produce. Therefore, it has a very high price. We also looked at the effect of raw materials that are crude and the possibility of moving from highly purified raw materials to fabricate membranes towards crude biomass, and how that influences the membrane morphology and the performances. So now I'd like to thank the group members who contributed to these projects, mainly Rifan Hardian, who's a research scientist in my group. Where is Rifan? Rifan here. Chongyang was a PhD student, graduated 2 years ago. She made an excellent job on preparing these membranes. Also, the Janus membrane was done by Victor, and Joyce prepared the biomass-based membrane using algae. I would like to thank the collaborators, mainly Eugene Chen, and the financial support from KAUST and the different companies who funded these projects. And at the end, I'd like to thank you for your attention, and I'm looking forward to any questions that you may have.
Okay, thank you very much, Gyorgy, for the very nice presentation. Participants who would like to have make a question to Gyorgy, just type on the chat, and then I will pass the question to him. Actually, there are no question yet, so maybe I have just a question to you based on your experience. I was wondering, how long do you think it will take to use this at commercial scale, let's say, these greener membranes? There are many weak points or to overcome, still overcome before their full commercialization at a big scale.
Yes, I think that's a very good question, and there is no, direct answer or straight answer that I can give to that. When will it happen? I don't know. So one issue is the reproducibility of these materials, right? That I also mentioned during my presentation. And the other issue is the provision of these raw materials at large scale with the same quality. So we were looking into prototyping some of our membranes and scaling them up. But then we realized that some of these green solvents are not produced on large enough scale for industrial membrane manufacturing. The other issue with certain type of green solvents is that they tend to age over time, so their shelf life is shorter than other solvents that are usually used for membrane manufacturing. So I think it will take time, but if the regulatory authorities they push for it and they give incentives to these companies to look into the deployment of green solvents, green materials, then it will be rather sooner than later. But on their own, I think companies, if they have already a way of manufacturing their membranes, just because of sustainability reasons, I don't think that they're going to make that step.
Okay.
And currently, the performance of these membranes are competing with fossil-based membranes, but their lifetime is probably shorter. So overall, it's not that easy of a choice for companies to move away from the well-known materials.
Yeah, sometime. Thank you. So in the meantime, I see there are some questions, so I will read it for you.
Okay.
So sorry for my pronunciation. Zulfikar Hamad Renhan wrote, you mentioned bisphenol in slides as green material, but bisphenol is toxic in nature. Will you please explain a little bit how to use it?
Bisphenol,
Bisphenol.
I don't recall bisphenol. Which slide was that? If you're still online, or do you remember?
It's not the number of
Alessandra.
slides.
because I don't see bisphenol. I can share my slide again. So if you look at maybe there is a confusion with
The
the
name.
chemicals. Because if we look at this, then on the left-hand side, you can see my screen, right?
Yes.
Okay, so on the left-hand side, we have the more traditional TFC monomers that are not really green, and some of them are indeed toxic. And the ones that would be the green replacement are on the right-hand side. And these are polyols that you can see here, which are natural materials. Also chitosan that you see on the top, or preamine that you can see at the bottom. But these are not bisphenol compounds.
Or maybe it's just written down biophenols. Maybe it could be this, maybe it was just he understood the bisphenol rather than biophenols. Maybe it could be, I don't know. Maybe it was...
Yes, I mean, if we are looking at this on the right-hand side that are proposed as green alternatives, then, we go into the discussion whether something is green or not, and nothing is green. These can be greener than other type of raw materials. So ultimately, there is no, green material or sustainable material. I'm pretty sure some of these are toxic, just like every other chemical or material that we use.
Okay. Okay, thank you. So the other question is from Edith Lecomte-Norin. Do you think that it is possible to use your membrane for biomolecule separation purification?
I believe so. I mean, at the moment, we are actually working on mRNA purification, which is one of the latest applications that we are interested in. So yes, they can be. I mean, some of these membranes, I mean, those are usually made in aqueous systems. So the environments are not as harsh, and usually the compounds that you want to separate are much larger than traditional pharmaceuticals with small molecules. So in that sense, the separation itself is easier in terms of selectivity. However, the fouling or biofouling issues can arise in that case.
Okay, there are two more questions. Maybe we try to be fast. So from Vikas Pundir, is there any chance that we can use these green membranes in flow reactor or electrolyzers as an ion transport medium? And how durable will they be?
Good question.
Oh, I just brought a new one. Right now, membranes are the consistent part in the electrolyzer system. So is it possible to make cheaper ion conducting or transporting green membranes? Because it will definitely reduce the energy cost.
Yes.
It's the same person making the question.
Yes, and it's a very good question. We are trying actually to work in this area as well, but so far we were not successful. So we do not have any membranes that are suitable for this, unfortunately. But it's a good idea, and I know that several groups are working in this front.
Okay, thank you. So the last question is from a CapEx perspective. There is not the name of the person, but how will the cost compare with a conventional membrane system? So it refers to the economic part of the
Yes, I mean, in terms of CapEx, I mean, the membrane housing and the whole unit, how you apply these membranes and the process itself is the same. If you refer to the membrane material, the membrane material price can change. As I said, that the solvents sometimes are more expensive than conventional solvents, but not in all the case. So there are many green solvents that are the same price or even cheaper than conventional solvents. The raw materials, it depends. If you manage to get some biomass from waste, then I believe that will be much cheaper than any commercial polymer that is used nowadays for fabricating membranes. Here, the scale could be an issue, that if you want to work with biomass that is not produced on such a large scale, then although it's cheaper or it has a competitive price, then you just cannot produce the membrane on large enough scale.
Okay. So thank you very much for your kind presentation, and
Thank you.
so wonderful presentation also from Vikas Pundir, and I think everybody appreciates. So thank you to stay with us. And now we can move to the second speaker of this webinar. It's my pleasure to introduce Dr. Giuseppe Barbieri from the Instituto of Membrane Technology in Italy. And he will talk us about the valorization of hydrogen in e-fuels by membrane operations. Please.
Thank you very much, Alessandra, for your kind introduction. Do you see the screen?
Yes.
Do you see the screen? Okay.
Yes.
Okay. Chemical storage of hydrogen, in particular in e-fuels and using membrane operation. Why? We have. I am starting from the fundamental source, the main source of renewable energy. That means the sun. The sun. We have the renewable energy on the earth, you know, by production of electrical energy by photovoltaics. But we have a problem of storage because we produce electrical energy, but here still missing the storage of this energy. Or, you know, we know also the wind, because we use the wind since long time for our ship. Here there is Amerigo Vespucci, a sailing ship of Italian Navy, is for training ship for students and military people. Then the wind is was used since a long time, because, you know, windmill is one of the use of that, where wind energy is transformed in mechanical motion, but without any storage. Or nowadays we have wind turbine. That means anyway we are producing electricity, but there is an issue about the storage of that. You know why I am speaking about storage of energy? Because during the day, this is is known as duck curve. That means the amount of energy produced and the one used during the day. And if we reach the production, the balance go in this area, we have instability of the energy system. And during the day, this is the energy this difference that we have depending on the year. We have some report year by year, and if we go in this area, we have some problems because the production is not enough for the utilization. During the night, however, we have much larger energy production, or early in the morning, early in the morning or during the night, we have a lot of energy. And this energy production we don't use, because during the day we need energy for human activity, but during the night we don't have a need. Also, we have solar production that is only during the day because we need sunlight. The wind maybe we can have also during the night, and depending on the weather condition. However, this is, one of the concepts coming from here is that the production has to be higher than utilization, but how much higher? We will answer to this in a few slides. Energy harvesting and storage is an ancient issue. We needed energy since long time from the human world. So also, water, we use the water for mechanical motion, but here there is no energy storage. We have energy storage using dam, where we collected the water with the wall, and then we preserve the potential energy of this water, and this is one of the example of energy storage. Another example of energy storage is the electrical energy. We have some, battery, small one, bigger one, little bit bigger, and also, big system for energy storage. But this energy storage system is enough for, for the necessity of industrial plant, human activity, and so on. everywhere. So electrical storage remain an issue, for the sites that we need for that. And here, come the issue about why hydrogen, or, we are going to chemical system for storing energy. The first step is the production of hydrogen, because we have energy, and then with, by electrolyzer, we can produce hydrogen, green hydrogen that can be stored also for a long time, because hydrogen we can store for a long time, hydrogen, and also transport at a distance and transformed in other energy carrier. So hydrogen become a bridge between, energy fluctuation of the renewable and the demand that we can have, the demand of energy that we can have every day. So it becomes also a solution for storing energy. And for storing energy, for instance, during the night, we can have, the production of energy during electrical energy during the night, and then, producing hydrogen and store that. However, what is about new hydrogen? It's not a new molecule, not energy source, is, energy vector. It's a green fuel. This is quite good, because in this case, we don't produce an extra carbon dioxide. Renewable energy is abundant, but is intermittent. This is one of the problems. So hydrogen can be used for converting the excess of power in flexible energy. And however, we have a more complex system, but it's not so big issue as well. What is the drawbacks of hydrogen? The drawbacks of hydrogen is its energy density, that is, 3 kilojoule per liter. So we need another solution for having higher energy density. So e-fuels like methanol, dimethyl ether, ethanol, kerosene, and diesel has higher energy density. In this case, I highlighted the dimethyl ether energy density, that is 19 megajoule per liter, much higher than the 3 kilojoule per liter of hydrogen. So this can be one of the e-fuel that we can consider in our study. Also, these e-fuels are liquid at room condition. Hydrogen, as you know, is gas, and is, complicated the storage of hydrogen and facilitate the storage of this liquid system. Also, we can use existing infrastructure, and also, we can keep this chemical for long term, in the long term time. Also, from carbon point of view, is carbon neutral, because we have to use carbon dioxide, for instance, coming from a biogenic or other carbon source. So here, is reported an example of what can be, the integrated energy system, because we have from one side electrolysis, then we can have here, for instance, methanation of carbon dioxide. For methanation, we need hydrogen, or hydrogenation of carbon dioxide to e-fuels, and in the other we need still hydrogen. Also, we can transport hydrogen from long distance using pipelines for natural gas. In this case, we have a complex system that can be transported, and then we have to find a solution to recover it, the hydrogen, but is out of the present work. So what are the membrane operation we are considering in this presentation? Is membrane gas separators and membrane reactors for high or low temperature, or and also catalytic membranes. So why dimethyl ether? Dimethyl ether, is not toxic. Used in a blend with LPG, can be used for that. Also, it's important chemical intermediate for the production of olefins. Also, is used in aerosol for propellant in spray can, and so on. Also, is an alternative fuel additive. Why additive? Because it's an ether, and so is very volatile, and so it's better to use as additive to diesel, for instance. So what is the main reaction step? For dimethyl ether, we have two reaction steps. The first one, the conversion of carbon dioxide and hydrogen in methanol. And here is also reported the operating condition, 250, 300 degree and pressure around 350 bars, 30, 50 bars. The second step is the iteration of methanol to dimethyl ether, where we have dimethyl ether and water is one of the issues that we try to face today. And the temperature is 200, 300 degree and the pressure up to 20 bar. In this case, we can valorize carbon dioxide and hydrogen. So carbon dioxide can be, for instance, from the waste municipal, organic municipal waste from the anaerobic digestion of these that produce methane, and then we recover from methane from one side and carbon dioxide on the other side, and so then we can have the first step, methanol production, and then dimethyl ether. For dimethyl ether production, we need hydrogen, and hydrogen can come, for instance, from electrolyzers, so green hydrogen can be used for that. So there is the missing, element in this cycle is just hydrogen. So, looking to the second step, the results that I am going to present here is related to the second step, the relation of methanol to dimethyl ether. So the reaction, this is the temperature, is not particular high temperature. Also the pressure is not very high one. The catalyst, some catalysts already exist. For instance, alumina catalyst has chemical, thermal, and mechanical stability, low cost, and high selectivity to dimethyl ether, also at high temperature. Zeolite, such as ZSM5, B, and so on, also is chemical stable, chemical, thermal, and mechanical stable, and has strong acid side, favoring fast methanol conversion, also at lower temperature. So, however, there are, some drawbacks. Alumina, for instance, has a strong absorption of water, one of the reaction product, and consequently can deactivate the catalyst. The zeolite can have the formation of coke at temperature higher than 260. And consequently, also in this case, we have the activation. So the question is a new strategy in the use of this catalyst, for instance, differently designed, or with a different morphology, in order to keeping the methanol conversion and the selectivity to dimethyl ether for longer time? So the answer is that we have in mind to use catalytic member or contactor because in this case no separation function is used of these materials. So this is we call membrane, as can be used for separating components, but in this case we use just for contacting the methanol and the catalyst. And so we can have on one side we feed the reactant methanol, and on the other side we have, we collect the products, the methyl ether and the water, and unreactant methanol. So no separation factor is used in this case. However, can be have some advantages such as enhanced mass transport of reactant and products, because both are in the same direction. On the contrary, that happens in catalytic pellet, where we have diffusion on one side and back diffusion of products on the other side, on the other direction. And the continuous removal of dimethyl ether, of the products from catalytic side, can limiting the catalyst activation, so we can have catalyst activity for longer time. We believe that we can have these advantages from this material. Here there is a scheme of the experimental apparatus, and we feed methanol on one side of the membrane, and we collect the methanol, the dimethyl ether and the water on the other side. So here there is a long list of some membranes that we already tested, and you can find ZSM5 zeolites or supported on alumina or titanium or via membrane. and also gamma alumina membranes, with some different thickness, for instance, 50 microns or 63 microns, or thinner membranes with 6 micron in total as as thickness of the of this material. Some membranes has also 2 different layers with different catalytic acidity or silica alumina, silicum aluminum ratio. So here there is just some information about the first 2 membranes we tested, ZSM5 supported on aluminum and titanium. The silicum aluminum ratio is the same porosity. The thickness is a little bit different. Reaction volume so is different because for the length and for the thickness of the material. And the membrane area is also different because longer membrane allow us longer membrane area, and you can see here 23 centimeter long against 7.5. This membrane we buy from EKTS in Germany. Here I reported briefly the operating condition, the temperature and the pressure, and also feed flow rate is very, very small because the catalyst volume is very, very small. It's just the thickness. I show you sometimes it's 6 microns, sometimes it's 60 microns for the surface area that we have is not so big, not so large amount of the catalyst. So we have a very, few microliter per minute of methanol feed flow rate as a liquid. Some results. The conversion of methanol is very, very high. Depend on the, when we reach 200 degrees, for instance, the right temperature for this reaction, we can have a very high conversion. TREC means traditional reactor equilibrium conversion. So we reach the equilibrium. We are approaching the equilibrium in this condition. When we increase the space velocity, of course, the catalyst started to become, the rate determining step is smaller with respect to the feed flow rate, and so we decrease the conversion, increasing the space velocity. The similar results we have, when the membrane is supported by titanium. Here, in the right figure, we don't have the space velocity of 1 hour minus 1, and so. But if you compare the 2.2, the space velocity of 2.2, the results for this, and the results on the left side for 2.6, they are very, very similar. These measurements. So a comparison with literature show that the membrane is a little bit better than a conventional system. Here the comparison is done for higher space velocity because we find in the literature results for a space velocity of 2 hours minus 1. And however, you can see that the results for catalytic contactor is better than the porous pellet. Then we also tested, characterized, used some membranes supplied us by Chung-Ang University, that is in Korea, in Seoul, South Korea. Here there is some information, some also result characterization of these membranes, and the operating conditions are very, very similar to the one. This is the first results are using via membrane supported on aluminum membranes, and you can see that at the lowest space velocity 3.5, more than 3 times than I showed you before, we have the equilibrium conversion. We achieved the equilibrium conversion really, really high. Also, at the lowest temperature, the BIA is much better than ZSM5 as catalyst, and by increasing the space velocity, of course, the limiting the small amount related to compared to the flow rate is important, and we have lower conversion. At higher temperature, the catalyst is more activity from kinetic point of view, and so we have higher conversion. You can see also on the right side that the conversion of methanol decreases much more when the temperature is lower than at 204 degrees. In any case, we have a selectivity 200%, 100% to the methyl ether. No other component we measured in our gas chromatograph. Another important test is what is the effect of water on the catalyst, because if the methanol coming from the first step of reaction where we have CO2 and hydrogen, we produce CO2 and water, and in this case we don't have pure methanol such as we can have in the lab, and it's important to evaluate the effect of water, the presence of water inside of the feed. However, you have to consider that the total feed flow rate in the first blue condition, red, gray, and so on, is always 1 microliter per minute. This means that when we have the red results, we have not 1 microliter minute of methanol, but 0.8. And so we have lower conversion for the presence of water. And also we expected higher conversion because we have lower amount of methanol, but the water, affects significantly the conversion that we have in the reactor. When we increase furthermore the water content, we have an extra reduction of this. And when increase and we feed 1 microliter of methanol and 1 microliter of water, the conversion is very, 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 very low. Then, what about the stability? The stability, depending on the temperature, we can see, you can appreciate that when we have, operate at 200 degrees, we have a conversion, a stability in methanol conversion for about 8 hours. When we increase the temperature to 240, we have shorter stability, and also the stability is shorter when we increase the space velocity, that of methanol in the reactor. However, when we compare these results with some results of the literature, here we have this is a higher temperature because we also the results in the right figure is at higher temperature. Literature results of after 5 hours there is no more significant conversion. We have significant conversion also for after 50 hours, so higher stability than the one in catalytic pellet. And also we recover the performance of the catalyst with a thermal treatment with nitrogen. We feed nitrogen instead of the reactant, and we recover the performance of our reactor. Here there is a comparison between the alumina, in this case just another test on alumina membrane, that is at the beginning as a lower conversion, show lower conversion than the alumina pellets, but its stability is for longer time. Bilayer membrane, our partner colleague in Seoul, South Korea, prepared bilayer zeolite membranes where with one layer more with higher silicon aluminum ratio, and the other one lower, and the other one with higher. That means lower acidity and higher acidity. And you can see that you can appreciate depending if we have membrane 1 that we met before, when the feed met before, the lower acidic layer, and then the most acidic layer, we have the highest conversion, membrane 1, with respect to membrane 2 that meet before the first acidic site layer and then the second one. So What about the stability? You can see that the membrane number 2 is the one that I showed you before, and is very stable over the time. The first one is showed, a decrease in the conversion, but in any case is quite good also this one. And here there is just a list of some results. Here there is methanol conversion very high for some membranes, and however you have to correlate it with the gas hour space velocity. When we have the right gas hour space velocity for alumina, we have the high value of conversion. Vice versa when the ZSM5, sorry, and when the space velocity is too high, we have lower conversion. For BIA is very high because it's better catalyst, and also for gamma alumina is a really interesting conversion with the appropriate gas hour space velocity. Now I would like to introduce, not a reactor. We are not in this case prepare, keeping the hydrogen, valorizing hydrogen, or make chemical storage, direct chemical storage of hydrogen. The reactor is a methanator here, and the membrane. What is the function of the membrane in this case? The reactor, not all the time, all reactor convert all the feed, all the reactant that we have. Sometimes we need to recover the unconverted reactant and to recycle to the reactor. This system, and in this case, membrane is gas separation unit here. These membranes can be, used for treating the downstream. And in this case, the treating of downstream allow us to increase the total conversion, the total yield about methane. In this case, the methane is reach also, 97.5% in concentration, and starting from 60, and the other coming from carbon dioxide and hydrogen. So this is another valorization. In this case, membrane operation does not work directly on the valorization, on the hydrogen storage, but help supporting the carbon storage. This is one of the, considering methanation, and the other one is, also considering a reactor for producing methanol. In this case, there is a downstream treatment and also upstream treatment, and converting the carbon dioxide coming from the inlet, in this case we are considering biogas. Methane is separate in the upstream, and then carbon dioxide go inside the reactor and is converted in methanol. 40 mole of carbon dioxide is converted in 38 mole of methanol. So just some concluding remarks. Membrane operation play an important role in chemical storage of hydrogen. The characteristic of catalytic conductors membranes allowing themselves to cross it by reactant and reaction products flowing in the same direction, allow an increase of the catalytic stability over the time, open the use of some materials, for instance, gamma alumina, that as pellets is not operated, cannot be used for methanol conversion immediately, show high methanol conversion, very, very high, close to equilibrium 1, and excellent selectivity, close to 100% to demethylator. What about the other membrane operation, gas separators? Are a values for supporting solution, as they contribute to separate a reactant fraction and recycling it in the reactor for improving conversion. I would like to acknowledge some project, Grifus, Hydromine, Tech4U, and ADP Hydrogen, some colleagues, Adele Brunetti, Elisa Bruscio, and Luigi Marsico, and also the colleague from Korea, and all of you for your kind attention.
Okay, thank you very much, Giuseppe Pino Barbieri for this nice presentation about the different way you can improve the performance of the processes playing with membranes. We are a little bit late, but we have a question, and then I would like to read it for you. The question is, in the methanol to DME reaction using a catalytic membrane, does the produced water impact the catalyst activity, given that it may affect the available reaction surface area?
The answer is yes. However, there is an effect of water, and is one of the aim of the work. However, what is the extent of this effect? Is higher or lower than the one that you have in catalytic pellet? We believe, and we measured lower effect, lower extent of the water presence in the catalytic membranes, because the mass transport in the same direction, because both reactant and products flowing, for instance, from left to right, both transport the water in, and you don't have to use just back diffusion, because in a catalytic pellet, in a pore of catalytic pellet, you have diffusion from reactant from left to right, and back diffusion of reaction products from right to left. So we have not just in the membrane, we don't have just diffusion as mass transport, but diffusion and convection, and these help us to remove the water.
Okay, thank you very much. And now, just for question of time, there is no more questions. But if you have, of course, you have also the contact of our speakers. You can contact them later on. We can move to the last presentation. Last but not least, it's a pleasure for me to introduce Professor Maria Norberta dePinho from the Universidade de Lisboa in Portugal. And she will talk about recovery of biomolecules from winemaking byproducts, a path towards circular economy in the wine industry. Please.
Thank you very much, Alessandra. First of all, thank you also to Martin, and thank you very much for the organization and for the invitation. Thank you very much. Okay, I will start speaking about the recovery of products from the waste streams in the winemaking process. Yes, and the wine production, as we know, starts with the grapes, and the grapes, after a series of operations, give the grape must, and the grape must is fermented, and we have the wine. And the wine is stored in tanks, and this storage, it's simultaneously a sedimentation operation. In fact, during this storage, we have the buildup of the bottom of all the suspended and the colloidal matter that goes to the bottom, and this bottom of the tanks is the lees, and these lees are very important, as they provide a lot of polysaccharides and polyphenols. And the polysaccharides, we can have monoproteins, and the polyphenols, we have tannins and anthocyanins. So we have very valuable products, but the concern with the lees and the recovery of these products from the lees, it's also because the lees are generated in large amounts. In fact, for instance, for a production of 270 million hectoliters of wine, we have the generation of we have the generation of 1.2 million tons of lees. So we have here a large amount of lees and the recovery of very valuable enological products. Okay, so how to get this recovery? We will develop membrane process, based membrane process that is a sequence of membrane operations from microfiltration, and the microfiltration essentially remove the colloidal matter in the retentate and produce a permeate that is the feed to the ultrafiltration operation. And in the ultrafiltration operation, we will have the concentration of the polysaccharides and a permeate that goes to the nanofiltration as a feed of the nanofiltration to concentrate the polyphenols in the retentate and produce water that can be further purified through reverse osmosis, or can be as such even used in the cellar, depending on the quality of the water that it's necessary. Okay, so this process, what we have, starting with the microfiltration, we will use in the microfiltration hollow fiber membranes that they are from PAM. PAM is a Brazilian company, and these hollow fibers membranes, they have a pore size of 0.4 micrometers. Then the ultrafiltration and the nanofiltration, we are using commercial membranes from Alfa Laval in the WEF, and the Alfa Laval membranes that we are using have a molecular weight cutoff of 1000 Dalton. Then in the nanofiltration, we are using FilmTech membranes, and these FilmTech membranes have a molecular weight cutoff of 400 Dalton. Okay, these are the membranes, and now let's go to the operation. The microfiltration operation is run in concentration mode, and that means that we have the concentrate, the retentate, and the permeate back to the feed tank. And this microfiltration, I must say that the feed from the lees is diluted 10 times. So we have simultaneously an extraction in an aqueous solution together with this microfiltration operation that separates the colloidal matter, or the residual suspended matter, and provides a permeate that is further processed by ultrafiltration. Okay, so we will have this microfiltration being processed at 0.5 bar, and a feed solution circulation of 150 liters per hour. Okay, and we will have the microfiltration running at different volumetric concentration factors. That it's defined, the volumetric concentration factor, as the initial feed volume to the retentate volume. Okay, the final retentate volume. And then we will define the rejection coefficients as the concentration of the component that we are studying in the feed minus the concentration in the permeate divided by the concentration of the feed. Okay, and then we follow for the ultrafiltration and the nanofiltration, and these operations are run in total recirculation, no, in total recirculation mode, and we will have operate the ultrafiltration at low transmembrane pressures and the nanofiltration at higher transmembrane pressure, and all of that in the range between 3 and 15 bar, and with feed circulation velocities corresponding to flow rates of 100 to 200 liters per hour. And of course, we will define the rejection coefficients in the same way, the concentration of the component that we are studying in the feed minus the concentration in the permeate divided by the concentration of the feed. Okay, and all of that had to be assessed with analytical methods that go from the total organic carbon, the total suspended solids, the turbidity, to the total polyphenols content and the total monomeric anthocyanins. And we measured also the antioxidant activity in the different permeates. Okay, and one important thing, always with membranes, when we have the membrane process, we are always concerned about fouling or trying to avoid the fouling. And the fouling really, it's there is a precursor of the fouling that it's the concentration polarization. So we will try to optimize the two parameters, the feed circulation velocity and the transmembrane pressure, in order that they will lead to minimization of the concentration polarization. And to quantify the concentration polarization, we will have experimentally measured the mass transfer coefficients. The concentration polarization, it's nothing more than the buildup in the boundary layer adjacent to the membrane of a concentration profile. So we will have at the membrane surface concentrations higher than the average concentration of the feed. And we are trying to minimize this augmentation of the concentration near the membrane, and that minimizing these concentration profiles through mass transfer coefficients, higher mass transfer coefficients that can give back the material concentrate that the interface to the bulk and to be removed from the retentate. Okay, so, and to get the experimental mass transfer coefficients, we use the pressure variation method. That it's a classical method of chemical engineering, where we plot the logarithm of 1 minus the rejection coefficient divided by the rejection coefficient versus the permeation flux. And and that will give us a straight line whose slope is the inverse of the mass transfer coefficient. And here we will have the mass transfer coefficients in this right-hand diagram. We will have for 3 circulation velocities and in the range of permeate fluxes from 1 10 to the minus 5 to 3 to 10 to the minus 5 meters per second. Okay, so having that in mind, let's see at the results. And the first thing that we did, it was the characterization of the effluent in terms of the total organic carbon, in terms of total suspended solids, total of polysaccharides and the total of polyphenols and the monomeric anthocyanins. And we have in this table the values of these characteristic values of this effluent from the second racking. Okay, and now we characterize the membranes and the nanofiltration and the ultrafiltration membranes. We characterize them in terms of the hydraulic permeability in kilograms per hour, per square meter, per bar, and in terms of the rejection to salts and to sucrose. And obviously, we have for the ultrafiltration for the ETNA membrane, for the ultrafiltration membrane, much lower values to the rejection coefficients than the values for the nanofiltration membranes. And for the nanofiltration membranes, we have a characteristic pattern that is for sodium chloride. We have lower values of rejection than for sodium sulfate. And that is characteristic of the nanofiltration membranes. And we have two sucrose rejection coefficients of completely total rejection or close to that 90% of rejection coefficient. Okay, and then for this characterization, we use pressures of low pressures of 4 bar and feed circulation flow rates of 150 liters per hour. And solute concentrations in the feed of 2 grams per liter. And now let's see the first results of the microfiltration. As I said, the microfiltration is run in concentration mode, and as we can see, when we increase the volumetric concentration factor, we will have flux decline, the permeate flux declining, and it increases, this decline increases with the increase of the volumetric concentration factor. And in fact, we can see that at a concentration, volumetric concentration factor of 3 or higher than that, we have a plateau. So we have for the lower pressures, lower volumetric concentration factors, first decline, and then we tend to a plateau for the volumetric concentration factors higher than 3. Okay, so then, as I said, the microfiltration in concentration mode, we have here a graph that we present, again, the polyphenols, the amount of polyphenols in the permeates, depending on the volumetric concentration factor. And we have, as the volumetric concentration factor increases, we have an increase of the amount of polyphenols in the permeates. And we have here also the recovery products, the recovery of the products for the polysaccharides and for the polyphenols and for the monomeric anthocyanins of running from 5 to 20% to 50%. Okay. And that, this, as I said, the microfiltration or the permeates of microfiltration provide the feed for the subsequent operations of ultrafiltration and nanofiltration. And let's start with ultrafiltration, and I will be back to the, and in ultrafiltration, as we know, we have always, for low transmembrane pressures, a linear behavior of the permeate fluxes with the transmembrane pressure, and then it curves, and we have these values always lower than the value of the hydraulic, the corresponding values of the hydraulic permeability. And as we can see also in this figure, we have for the different velocities, feed velocities, for higher velocities, we have higher recovery, higher permeate fluxes than for the two lower feed velocities of 100 liters per hour and 150 liters per hour, that they are more or less in the same curve. Yeah. Okay. So as expected, we gain always with having higher feed circulation velocities and lower pressures. And that always in terms of minimizing concentration polarization and avoiding further development of fouling. Okay, so the nanofiltration, we have a different behavior as usual, and we have a linear behavior in the whole range of transmembrane pressures from 3 to 15 bar. We have the permeate fluxes varying linearly with the transmembrane pressure, and with a lower value that the corresponding values of the hydraulic permeability, but not so much lower as in the case of the ultrafiltration. Okay, so going back to the concentration polarization, or to avoid the concentration polarization, and getting the mass transfer, the experimental mass transfer coefficients, we try to correlate them with the feed circulation velocities through the Reynolds numbers and through the Schmidt number, the physicochemical properties of the feed. And we are here having a different, in chemical engineering, we usually have these mass transfer coefficients, or the Sherwood numbers, that are the A-dimensional mass transfer coefficients in function of the Reynolds and the Schmidt numbers. And that it's always for impermeable walls, but a membrane by definition is a permeable wall. So we are getting these correlations with an additional A-dimensional number, that it's an A-dimensional hydraulic permeability, that it's A-dimensionalized by the radius of the membrane. Okay, and so doing this, the minimization between the experimental and the predicted Sherwood numbers, we get the minimization to give us a correlation with the Reynolds number to the 0.5, around 0.5 power, Schmidt number to 0.3, and the A-dimensional hydraulic permeability to 0.35. So we can have here the optimization of the best conditions in terms of feed circulation velocity and feed circulation velocity and transmembrane pressures. And that will give us, as I said, the values of the concentration polarization that we have here in this table the values are very low, very small, but we have here in this table for 3 different feed flow rates and or feed circulation velocities, and for each of these feed circulation velocity we have pressures, transmembrane pressures running from 3 to 15 bar, and we have here the concentration, the module of concentration polarization, so the increase of the concentration at the membrane surface, CAM minus CAP, divided by the concentration at the average concentration in the bulk of the feed minus the concentration in the permeate. So as we can see, to have low or to have no concentration polarization, we will have to have 1, the value of 1. We have, as we can see here, for we have the values closer to or more close to 1 when we have the higher feed circulation velocity and the lower transmembrane pressures. Okay, so that it's important in order to run these operations in conditions where we minimize the concentration polarization and further avoid fouling. Okay, so these were the values for the nanofiltration, and here we have the values for the ultrafiltration, and we have also the same trend that for higher feed circulation velocities and lower the values of transmembrane pressure, we will have really values closer to 1, so minimizing the concentration polarization. Okay, so now let's see the results of nanofiltration and ultrafiltration in terms of the polyphenol rejection coefficients, that obviously they increase with the pressure, and we have in the right hand side for the ultrafiltration, and we have in the left hand side for the nanofiltration, and these rejection coefficients increase with the increase of the pressure. Okay, and the pressure range, as we can see, is in from 3 to 15 bar, and the feed circulation velocities from 100 to 200 liters per hour. Okay, so now the important thing is really that we have the ultrafiltration that has the capacity of fractionating the polyphenols from the polysaccharides. In fact, as we can see in the red, it's a red that is almost brown, we have for the polyphenols and the polysaccharides a big difference on the rejection coefficients. And that does not happen in the nanofiltration. And in nanofiltration, I have always high values of polyphenols, anthocyanins, and polysaccharides rejection. And we measured the antioxidant capacity of these permeates, and as we can see, obviously they are much higher in the first permeates of the microfiltration. And then we have in the nanofiltration, we have very, very low, in the permeates, very low antioxidant capacity, because all the as we said, we have the retention in ultrafiltration of the polysaccharides fraction, and the permeates with the polyphenols are feeding the nanofiltration, and the nanofiltration retains all the polyphenols, so the permeates of the nanofiltration will be depleted of the polyphenols and anthocyanins and all the compounds that they are responsible for the antioxidant activity. Okay, so I think that I am concluding exactly what I just said, that microfiltration in concentration mode presented high productivity with permeation fluxes around 25 kilograms per hour per square meter at a volumetric concentration factor of 3. And the product recovery at the microfiltration permeate, it's 25% for polyphenols and 50% for the monomeric anthocyanins. And then we have that this is the important feature of this sequence of operations. It's that the ultrafiltration has the capacity of fractionating the polyphenols from the polysaccharides, and the polysaccharides will be retained from this ultrafiltration membrane with the molecular weight cutoff that we mentioned of 1000 Dalton, and the polyphenols will be going through to the permeate. So we have permeates enriched in polyphenols and retentates enriched in polysaccharides. And I must mention that the polysaccharides, although we didn't give too much attention here in this work, but the polysaccharides are very important, and particularly the monoproteins can be very important enological compounds that can be recovered in this sequence. Okay, so, and in conclusion, we have nanofiltration with a high rejection coefficient to polyphenols and anthocyanins, and the antioxidant activity is predominantly associated to the polyphenols and to the anthocyanins. And as we saw, with this optimization of the operating conditions in terms of feed circulation velocities and the feed circulation velocities, and as well transmembrane pressures, we will have low values of concentration polarization. So we will have probably conditions in a long term not to have problems or severe problems of fouling. And I would like to give a special thank to my colleagues in Brazil and to this CITED, to this Ibero-American network that we have been collaborating for some time, and were very important in all this work. thank you to the financing of FCT and CFM, and to the Brazilian part, to the CNPq and CAPS. Thank you very much.
Thank you very much for the nice presentation. I think now it's a little bit late, so I don't see any question in the chat, but as I said before, you can always reach our speakers by emails for any next last moment question. I just have a curiosity by myself, just to know if do you plan to scale up your integrated membrane system for an application on a real scale? Are you planning something like that?
Well, not now, no, not. In fact, in 2 weeks, I will go to Porto to engineering, international engineering conference only on wine. So,
oh yeah, I know about that. I have heard.
You know about
Very
about the engineering conference. International, and I hope to talk with people and to be with among the wine people. No, we have not foresee any scale up. I must tell you that right now we had a lot of collaboration with the agronomy department in Lisbon, and right now we are focusing in de-alcoholization of wines. So probably it will come. I hope that it will. I hope that it will come, but we have to have probably to have some support from industry, and I hope now in Porto to talk with people and see.
Yeah, because it's very interesting. In fact, I'm seeing now also Ramsey Christian de la Rosa is telling the same great results. Do you think this can get to full scale industrial production soon? So the same question I told you. And there is another last question very, very quickly. Antonio Martin said, I missed a bit of the presentation, hence I'm unsure. Did you try it with material from real wine processing?
Yes.
Yes.
Yeah. It was a real wine, but Del Martin, this is wine in Brazil, from the region. Brazil has the region of wine close to Porto Alegre. And my colleagues in Porto Alegre worked with Alma. It was the company of wine production. So, in fact, this is not Portuguese wine. It's Brazil wine, but it was done with wine. And Alessandra, just to tell you that previously we have done this. Not the scale up, but we have done these experiments, but before with the Lab 20 membranes, Lab 20 unit that has much larger membrane surface areas. We can load the Lab 20 with membrane surface areas close to 1 square meter, which is very drastically different from these studies that we did here at the lab scale. Yeah.
So thank you very much. So time is flying, is running. And then I would like just to sum up. First of all, we learned, thanks to our speakers today, how to valorize leaves of grapes, hydrogen in e-fuels, and also how to move towards greener membranes in nanofiltration. So thank you very much for these very interesting lectures. And I would like to thank, of course, all of you, and especially all participants who stay until now, because it's quite late. Maybe somehow they have to leave at home back. So, but thank you for staying with us until now. We had an average more or less more than 100 participants. So very, very nice webinar. And Martin, I don't know if you want to add something more.
Oh, no, nothing. Just thinking thank you to all the participants and the speakers for this nice presentation. And I remind to the participants that if you want to have a look to the webinar another time, you will find the video on the EFCE YouTube channel at the end of the month. Okay.
See, okay, very good, because I'm seeing some questions about that. There will be recorded the video on the EFCE YouTube channel, so you can view again and again the video if you are interested. So thank you again for your kindness and interesting presentations. And thank you all participants for being with us.
Thank you.
Bye-bye.
Everyone.
Thank you.
Bye-bye.